Thank you, Rob. It was a pleasure that you invited me for this conference. And hello, ladies and gentlemen. I'm very happy to present this to you. And Rob gave me a hard work because he wanted to have an overview of our different minerals and additives in the concrete and in the mortar industry, which is a topic which is quite, let's say, large. So put on your safety belts and please, we go on with our product range. So what we are trying to do in Newchem is that we are trying to use minerals to work together with hydraulic system to improve the quality of the hydraulic concrete or mortars. Coming from the polymer industry, I was interested to see if we can do such things. Many years ago, we started to sell fly ash from Germany, and we got good customers, big quantities, which today are not possible anymore. And therefore, for the moment, we have been looking for other things. And when I came back from the world of concrete many years ago with metakaolin, we started to import metakaolin. Oh, something is gone. Okay. So what do we want really to do? We want to increase the life cycle of the concrete. And we want by this to produce slimmer parts using less material and less energy, resulting also in a reduction of the CO2. The second topic we are working on is avoiding cracks. Most books today tell that concrete has to crack and you have to use rebars to avoid the cracking and to hold the pieces together. Here again, we wanted to improve the life cycle of the concrete. We want to use less rebars because steel is a very big producer of CO2. We want to improve the aesthetics, and we want to reduce the CO2 again. So I start slowly with Pozzolana. These are well known today. We are converting the lime to a cement binder. Normally in the Portland cement reaction, you will get about 25% of free lime when you use a CEM1, and this can be reacted. And the Romans already building with lime in the past found out that if you added the pumice or the fly ash from the Vesuvio to your lime, you would get a bigger amount of non-soluble binders, as you have here in the Pantheon, which stands there for about almost 2,000 years. And here this aqueduct from Pont du Gard, where you can see that it stands almost as long and it carries water, and it still carries water. So taking into account this reaction, we tried different pozzolanas, and fly ash is naturally one of them. And metakaolin is another one. And by this, we produce more binder. So you have the same binder you would produce with your Portland cement. You add up new binder by using the reaction of your Portlandite. Now, what is a problem, or why do we use it? The first thing is maybe here on the left side, you can see the efflorescence. That means that the mortar which you use to stick your stones together, if you have some water pressure behind the wall, the water will seep through, will dissolve your calcium hydroxide, which will come on the surface. It will react with the CO2 of the air, and you will get these deposits which are not very nice looking. The same problem we have in Austria, we have a lot of tunnels, and the wastewater which are in the tunnels or sipping through the mountains have to be evacuated from the tunnel so that they don't build up pressure. And this is a drainage pipe from a tunnel, and you can see in the lower part here the calcium carbonate which has formed. About 16% of the maintenance of a tunnel in Austria, the costs are done by emptying and cleaning these pipes. It's a major cost of maintenance in tunneling. Building more strength into the materials, you can make slimmer bridges. I will not explain this to the Lafarge people who have been doing this since many years. So what are the effects? We bind the excessive portlandite or calcium hydroxide in the concrete. By this, we build more calcium silicate hydrate or more calcium aluminate hydrate phases. We refine the pores. We have heard today that the water ingress is not very good, it's detrimental. And normally with chlorine, also the migration of the chlorine is increased. So refining the pores means less water transport and less chlorine transport and a denser concrete. So what pozzolanic minerals are there around? Well, we have the natural ones, which is strass, phonolite, pumice, calcine clays. There are many materials on the earth, mostly mixes, and that makes it a bit difficult to standardize these products. As I told, we started with fly ash, which is not really around and much more. And we have heard in your conferences that the slag also is decreasing a lot, and microsilica is the same. So slowly these materials are in short supply. In any case, there are not enough materials around to really modify the whole cement industry. We are working with a calcined kaolin, which is called a metakaolin, which is a very good pozzolanic material reacting very fast. It is made up of silicium and aluminum, and we are working with mixes. These materials are there in large quantities. It goes from the south of England down to the Ukraine, to Germany, Czechia, etc. I visited some mines in Spain and in Italy. There are quite a lot of materials around. Normally it's accompanied by quartz sand, so we have to separate it and manufacture the metakaolin by a kiln. There are different kilns, which I don't want to explain now. I just want to show you one of these kaolin deposits in the US, where you have about 8 meters high, a very good and very clean kaolin, which in Europe we do not have so much. So where do you use it? The oldest construction was in a dam in South America, where people use it to increase their compressive strength and to make a denser dam. We use it also in pipes because the calcium hydroxide, as we saw, is leaching out and the porosity of the pipes would increase. So this gives a good product against this. The same thing was in lime binding. We have now done shotcretes in Austria where we could reduce the lime, the free lime, which is washed into these drainage pipes by about 2/3, which means that you can reduce a lot of your maintenance cost of the tunnels. By the way, we want at least to have a 100 years working life, which is easily done if you have no leaching. We have a lot of customers making precast and ultra-high performance concrete because building more binder naturally gives a better mechanical strength. And we are working a bit on the eco cements, trying to reduce the CO2 and improve the quality of the cement. Now, as we have heard in different conferences, the natural materials is the only thing which is available in large quantities, and therefore you can reduce your clinker. We have done some trials with mixes of limestone and metakaolin, which I'm going to show you. We can replace at least 25 to 30% of the clinker, so reducing the CO2, because neither the milled limestone nor the metakaolin by itself liberate any chemically bound CO2. So here we have 4 different mixes we made. We made a cement. 100% is a compressive strength which we compare. It's the pozzolanic index. We have here 2 graphs showing. The first one, the lower one, is the compressive strength compared to the pure cement after 2 days. And you can see that with metakaolin replacing cement, you can increase about your compressive strength about 10%. Then you can add some limestone powder to make it cheaper, or other pozzolanic materials, and to get to the same 2 days compressive strength as the original cement. If you add much more limestone, you come here beneath the values of the cement. But in the normally you measure the 28 days compressive strength. So you see with the metakaolin, you're about 20% above the cement. And even when you use some limestone powder, you are almost at 20%. And even using a larger amount of limestone powder, you can still be above your normal cement strength. Well, this is one of the topics we have been working now for the last 30, 40 years. Many people are working in that. And the amount in sales is increasing very strongly. And we are very happy with that. And we reinvested in trying to reduce the shrinkage and the cracking of concrete. Here, the same thing. When you have concrete, you have a water ingress, or you have efflorescence on the other side. If you use steel in your construction and you get cracks, then the water will go in, and with time, the iron will start to oxidize, expand, and you will break your construction. That ends up with costly repairs. One example from Austria, we constructed a bridge here, and after almost finishing the construction, cracks were formed underneath the bridge. Big lumps of concrete fell down into the valley. We are very happy that nobody was hurt, but you can see what effect cracks may have in the nature. So how can we reduce the shrinkage? Now, the standard procedure is to use products which make etching guide needles. With these, you can counteract the shrinkage of your cement. Some people use calcium oxide, which forms different hydration products. This is going through a solution product. We know that Lafarge has used systems with sulfates, calcium oxide or hydroxides, and to produce these etching guide needles. these hydration products. We have now also introduced magnesium oxide, because in China people are using a lot of magnesium oxide in dams because they realized that the dams would not crack if they add some magnesium to their cement. Now here we have some pictures. Here we have the calcium oxide, and here we have the portlandite, the calcium hydroxide formed. This is a reaction which is quite fast. And the problem with this reaction normally is that it happens mostly in the phase when your concrete is liquid. Therefore, you lose your expanding power. So we have modified these types to use retarded types, which will take a few hours or days more to react completely, and will also react when the concrete is already solidifying. Ettringite, this is our working horse since many years, which we use for concrete, which makes either expanding concrete, or which can also give concrete with good dimensional stability. Magnesium oxide, we started this about 3-4 years ago. This is normally a reaction which is very slow, and in the cement norm, magnesium is limited by 5% because it can give a late expansion after 10 or 20 years, cracking the concrete. So we looked into this problem. This is mostly because the magnesium which is in the cement is sintered, and therefore it will take a very long time to react. Either magnesium oxide or magnesium hydroxide are almost in water insoluble. So what you see here is a particle of magnesium oxide, and you see the crystal of the magnesium hydroxide growing on the surface. It is not a process which is going through a dissolution of the particles. We have now changed the calcining conditions so that the magnesium oxide is accelerated, and we can guarantee that in 90 days underwater, the whole magnesium oxide is completely reacted. We can make mixes now also, because depending on your application or the customer's application, people want to have faster or slower reactions. And with these 3 systems, we can play a nice tune on the piano. So where do you use it? In dams in China, for example. You can use it in parking lots, because in parking lots normally you make your surface on concrete. Then you normally wait until it dries out and it shrinks, and then you put in the walls, and the walls now start to shrink, but the ground is shrink already. So normally you get some cracks into the walls. The same is with cellars. And as normally the limit of the width of the crack, as we heard today, is limited to 0.2 millimeters, you have to use, again, rebars to keep it to that value. In Japan, where most of the ettringite systems are used, they use it a lot underground, because the sandy soil would let the water through if the concrete would start to crack. With some trials we have, or literature we read, with magnesium oxide, you can do some concrete self-healing. And this is because if your concrete dries out and the magnesium oxide is not completely reacted, and as soon as the crack is formed and water penetrates in it, the magnesium oxide will restart its reaction and form the magnesium hydroxide or other salts. and therefore the crack will be closed down. This is a pure chemical process. Conclusions. With our pozzolanic materials, we want to improve the strength, we want to have a longer life cycle, and we want to use less material. And naturally, we are looking for a CO2 reduction like everybody else is today. With our anti-shrink products, we are trying to reduce the cracks. By this, we also have a longer life cycle, better aesthetics, and a CO2 reduction. Now, what I want to show to you here is an application. Maybe today we should rethink about the concrete in different applications. These are fences which are used in Hungary to avoid that people are going over the rails at stations. And because they have these steel bars in it, they are cracking and being destroyed. These fence parts are very heavy, and we have been asked to reconstruct it. And on the right side, you see the solution we have found. First of all, we eliminated the rebars. We made a very high performance concrete. We used some glass fibers and some classified fly ash, which means that we take out the fines of the fly ash and not the coarser particles, giving a very good flow and a good surface. And these panels now can be put in place by 2 persons. And we want it because it's a much slimmer part and a much more lightweight part than the original material. So I thank you for your attention. It was really flying over the whole product. And I'm sure that if you are interested, you want to have a lot of graphs and figures, which I'm not able to give you in this short time. You can contact me at technical@newchem.org, or you can phone me on the mobile phone. We have also 2 home pages, one for the metakaolin called metakaolin info, and we have a second home page called anti-shrink info. You will find there a lot of more information. And if you look at Newchem info, you will find our products with the data sheets. And please contact me. We are happy to work with everybody, and we are happy to exchange also information because probably the next question you will have is it conform to any norm? Thank you very much, and I pass on to Rob, and they're waiting for the questions.
Thanks very much indeed, Denis, for a very nice presentation.